Alright, on page 10 of your interactive notebook, label it Graphing Piecewise Functions. And then you're going to take the foldable that I gave you today, or the piece of paper, and cut it out and just paste it on page 10. Give yourself a little bit of room so you can write the definition of a piecewise function. Okay, and so a piecewise function is a function that is defined by pieces of other functions over a specified domain. So here's a couple of examples of piecewise functions. Now that you know your parent functions, you can take pieces of them over specified domains and piece them together as one single function, even though there's more than one piece. So this is truly a function. It passes the vertical line test, so it is a function. This is your parent function x squared. This is your parent function absolute value of x, and this is your parent function x cubed. And you'll notice that they create this one single function, even though there's three pieces to them. And you don't get the full pieces of the functions as well. You only get a specific portion of it. Here's another example. This one has parabola for your quadratic. You also have your line, and you also have just a single dot sitting right here as well. Okay, so those are examples of piecewise functions. To graph a piecewise function, first of all, you'll notice that it tells you what domain is going to be for the piecewise function that you're going to be graphing. So one of the things that you can do is you can make yourself a table for each one of them. You do not have to show this step. This is just me showing you how to graph each of these pieces. So for example, for 2x plus 3, where x is greater than or equal to negative 2, you'd make yourself a table for values that are bigger than negative 2. For example, you can use negative 2, negative 1, 0, 1, 2, 3, whatever you want. But the starting point, negative 2, needs to be in there so you know where the graph is going to begin. You'll plug those x values into the equation, and then you'll get out the y values so you know what points to plot. Once you plot these 3 points, you'll have a closed circle at the beginning of this one because it is an equal to symbol. You'll connect your dots, and then you'll draw an arrow showing that it goes on forever. Now for this next one, it says if x is less than negative 2, you'll notice I still have negative 2 in my table again, even though there's not an equal to symbol. And this is so that when I go to graph this, I know where my open circle is going to start the graph. So the same thing is true. We'll take numbers that are less than negative 2, for example, negative 2, negative 3, negative 4. You'll plug that into the rule of negative x plus 2 because that's the specified domain it wants you to use. And then you'll have, again, points that you can connect. So when you go to graph negative 2, 4, even though there was a less than symbol, I know that I'm going to put an open circle there. So that's why I included negative 2 in my table, even though it did not say less than or equal to negative 2. Then again, you'll connect your dots and then continue graph. For example 2, you'll notice that I do something very, very similar. And so you can pause the video to fill this in. And then you'll notice on this one, for the top one, when I do 3, 6, 9, for this top one, numbers that are bigger than 3, that's just going to create a line that has a slope of 2/3 and a y-intercept of 0. But you'll notice that it doesn't start until x equals 3. So you'll plot 3, 2, you'll make it a closed circle, and then you'll connect your dots for the numbers bigger than 3. Now, when x is less than 3, you have a single y value. This is going to be a horizontal line at y equals 2. And so all of these values for 3, 2, and 1 are going to have 2 sitting there. And so you'll have a horizontal line at y equals 2. But please also note that whenever you go to 3, 2, there was supposed to be an open circle sitting here. And now since the open circle at 3, 2 was actually closed by the first graph at 3, 2, that open circle now will turn into a closed circle. And so you no longer have the open circle like you did in the first example. And then for the last example, example 3, it says when you go to graph j of x, at one single point, x equals 5, you have the y value of 3. So I'm going to go ahead and plot that, 5, 3. And you'll notice on the y-axis I'm counting by 2's, by the way. Okay, so we've got 5, 3 as a point that we're going to graph. I think I graphed this wrong because this 5 should be down here. It should be 5, 3 down here. I plotted that wrong, so I apologize. Fix that for me. And then for this one, this is saying I can use any value of any value that I want for my x as long as it's not 5. So I chose numbers to the left of 5, like -2, 0, 2, and 4. I chose the number 5 specifically because I needed to know where that open circle was going to be. So you'll notice that when I go to do this one, there's going to be an open circle at 5, okay, if I plug it in here. So I plug in 5 times -2 is -10, plus 1 is -9, so there's going to be an open circle at 5, -9, even though right here it said 5 is equal, when x equals 5, y is equal to 3. So I plotted the closed circle at 5, 3, but an open circle at 5, -9. And then I plugged in 6 as well for a number to the right. You'll connect those dots, and you'll have a single line. But at 5, x equals 5, there will be an open circle on the actual line itself at -9, and a closed circle at 3. And that is it for this page.